Good afternoon, everyone, and welcome to this webinar. I'm Marianne, and I will be your host for about an hour. So the topic of the day is bridging the gap between data and knowledge with the ensembler X. So the first part of this presentation will be the slides, and then at the end you can ask questions, and you will use the GoToMeeting panel to be doing so. So in this presentation, we will cover 6 different points. The first one is how to improve your work time efficiency. The second one is how to combine data from many sources so as to understand the system. Then we will see how we can understand the structure of the data with multivariate analysis and how it helps us to locate the root cause of process product deviations. Then we will see how to design more efficient processes and products. And finally, how we can predict the quality at an early stage so that we can detect soon enough a problem happening in the process. So that is the first point. So improve your work time efficiency. So the main thing with the ensembler now and the new version is that the data are organized. So when you start a project, you will have all the data set and all the analysis that will be placed in a tree and in the order that you do them. So here, for example, we have a data set with PLS, and then we have done a PLS on it, on the raw data. Then I can see I have an MSC model and a dataset with an MSC pretreatment. So what I did is that I applied an MSC to that dataset, and then I can see I did a PLS on it. And same thing with EMSC. Here I can see I did another pretreatment with a derivative and some models. And then at the end I predicted, and I guess I did a comparison between all the different results. So just at looking at my project navigator, I know what I've been doing last time. In addition, you can get more information about each part of the tree and each section. So for example, here I get information about a PLS model, and I can see exactly what I did use. So there was 415 samples, and the classification, the cross-validation method was random with 10 segments. I can edit some nodes, so if you have some node on all your models, you will be able to really know what you have been doing. Another way to see what has been done is to follow the audit trail. So in addition to the information that you can get in the tree, you can see things that have been deleted. So you have all the actions that are listed in order at the different time when you did the different actions. So this organization will help you to really know what's going on. Another way of gaining time is when you can preview the result of pretreatment, because pretreatment are very time-consuming to set the right parameters. So here, for example, we have a statistical derivative pretreatment, and there are different options. So for example, you have the derivative order, the polynomial order, the number of left side points, and the number of right side points. And if you change things, well, the result will be different. So if you change it and that you see in real time the result of your pretreatment, then you will be able to see which pretreatment you should do. And so you will not do a lot of pretreatment and see the result and then see what was the best. You can see it before you do the pretreatment. So to conclude on this little part, when you have organized data, it will save you a lot of time, because then you will know what you did last month on this dataset. And all the plots are also saved, so you can know which plot was helping you to find the results. In addition, the preview of the result helps you to not do things that you don't really need to do. So this way you gain time. The second part is combine data from many sources for enhanced understanding of complex systems. So because systems are a bit complex, you can get data from different sources. So in Scrambler, you can import data from different sources. So you have, well, on Scrambler file, ASCII, which is used for a lot of type of data. Then Excel, and then we have MATLAB, and then a lot of spectral formats, and also from databases. So we have instrument partner. So all the instrument from those partner, we can import the data directly to the Unscrambler. And we also have system integration partner, like SIM and CPAT. So as well, here we can get data from their system. So here is an example of importation from an OPC database. And as you see here, you have to select the computer name, then the server, and then you will be able to select some variables. So for example, I take this variable and I will preview it, and then I can just click on OK and it will be imported. So in the navigator tree, you can see all the data you can import. So when you have a lot of data, maybe you want to combine them. So you can combine them in the analysis. It means that you can have one data set for X and one that is set for Y, or you can aggregate matrices. So either you augment them, so you put first the variable of X and then the variable of Y, or you can append them. So then you have samples that goes below each other. So with this feature, it's very easy to see a relationship and create model between any kind of data. So they can be from different type, and they can also be from different stages of the process. So then you can get a clear understanding of what is going on in the process. So to continue on the understanding of the structure of data, we are going to see the fundamental of multivariate statistical process control. So here we have two variables, variable 1 and variable 2, and they have upper and lower limit. So what happens is that the gray part is what you will accept if you were doing univariate analysis. So here we have plotted the ellipses, this ellipse, which is the Outling T2 ellipse, and which represents a 95% confidence region. What you can see is that it doesn't really cover the same area than the gray part. So there are regions that will be acceptable in multivariate analysis, but that will not be acceptable in univariate charts. And you also have some regions that are acceptable by univariate charts, but are not in multivariate analysis. So this is used to create what we call the design space, and that will make that all the samples are conform to what is needed inside this design. So here we have more than just two variables. We have several variables, and we have defined a model and with our design space. So if we take an example, like here we have NIR Spectroscopy that is applied to the monitoring of granulation process. So what we do is that we acquire NIR spectra during the process, and what we want to do is understand the batch behavior and follow the process trajectory with PCA. So the granulation process is important to increase the particle size, enhance compressibility, improve hydrophilicity, and improve product homogeneity. The process has 3 stages. The first one is dry mix phase. So when you mix lactose and starch, it's about 2 minutes. And then there is a liquid addition phase. So we had polyvinyl polyolidone and water, and it lasts about 1 to 2 minutes. And then we have the last phase, which is granulation, 3 to 5 minutes. So what we did here is that we acquired NIR spectra every 2 or 3 seconds on 15 batches. So we had a lot of spectra, about 130 to 180 spectra per batch, and each spectrum was having 1,101 variable. So the first 3 batches are run at target conditions. And then on the other one there will be some changes. So to see the pattern, we will do a PCA model. So there was first derivative that was done on those spectra. And you can see that there are 3 types of spectra. And they represent the different phase. So here in blue we have the first phase, which is the mixing of lactose and starch. And then we have the liquid addition phase in red, and in green the granulation. You can see that there is more variation in the granulation phase than in the other one. So here we have the OH peaks that increase when there is the addition of water. And the CH bands are changing as well due to the binding. So if we look at the result of the scores of all the samples on the first PC, we can see that for each batch, so a batch starts here and finish here. So we can see that the 3 first batch, they look quite similar, and they have the same profile. Then batch 4 and 5 are quite different. Here there is something missing, and it's because there was no PVP that was added during the liquid addition phase. And for batch 6 we see that the profile is also a bit different, and that's because the target condition with longer granulation time. So if we look at the score plot for the 3 batches, we can see that they kind of are superimposed to each other, so all the samples follow a trajectory. So here we have the dry mixing phase, and here at the end we have the granulation, so the endpoint. And we can see it in 3D. So the trajectory, like that, you see the number are representative of the time. And here the granulation at endpoint. So with this very small example, we can see that the structure of a dataset can be revealed by PCA. And sometimes you need to do a pretreatment to reveal the structure accurately. So here it was spectroscopic data, so we did a pretreatment that was spectroscopic pretreatment, like a derivative. But even on other type of data, you may have to do some pretreatment, like standardization, for example. The next point is design more efficient processes and products. So, well, here the main tool is design of experiment. So the principle of design of experiment is how to perform the least number of experiments to cover the design space in an efficient way. So here we have x1 and x2, and we have minimal and maximal value for both of them. And if we are supposed to do 9 experiments, we can place them randomly and have this kind of experiment pattern, or we can place them in a very structured way. And here we have a new pattern. So DOE is for the structure way. So we use DOE because the approach one variable at a time, which was the scientific approach, is limited. So one variable at a time approach is when you have several variables and you want to see if one of the source is having an effect, you will investigate each cause separately, and all your conditions are fixed. So what happens is that we have x1 and x2, and the first thing you do is that you fix x2, and then you will vary x1. So as you see, it varies, and in red we have the result. So when we have the best result, we decide to fix x1 to that value, and then vary x2. And here things happen nicely, and we have the best result at the intersection. But if not, we will have to do more experiments. The problem is that it will never really find the optimum. So here you see that the same cross, and here is the optimal point that we found, and that's the best that you can find in this area. But the actual optimum is quite different. So the logical approach to DOE is first to set the goal of the experimentation, so you decide of your model type. Then you select the variable to include in the design, which will give you the design space, and then you select the responses. And from that will come the appropriate design. So here we have an example. For example, we want to maximize the quality of our cookies, and because it's an optimization, we want a quadratic model. And we have 3 variables that we can vary in x, so cooking time, temperature, and chocolate content. And for the responses, we want stability, best before date, the preference, and the cost. And knowing that, we know that we have to do a central composite design. So the DOE module in Ensembler is organized with tabs, and which tab is doing one function. So the first one helps you to give a name to the design, set your goal between screening with interaction, and optimization, and you can write some description. It also gives you some history, so it's the creation time. Then you have to define the variable. So you define the variable with their different levels. So here we have 3 continuous variables for the design with their different value here. And then we have 2 response variables, preference and cost. So it's very easy to set up. You just click on add, and then you set them with those boxes here. Then you go to the next tab, which is choose the design. So automatically, Ensembler will select the best design that is suited for your experiment, depending on your goal and the variable and their constraints. Then you can get some information about the design that is selected. Then the next tab is design detail. And here, for example, we had a fractional factorial, so you get the confounding pattern. And you can see, if you want, maybe you want to change from a different fraction of this design. It gives you some information about the number of experiments you have to run. Then on the additional experiment, you can add some center sample, replication, and some reference samples. Then we can change the randomization. And finally, we have the summary. And what is new in Ensembler X is that we have the power calculation. So we can calculate the power of the design for each variable if we know the standard deviation of the response and the minimal variation that we want to see. So when I set those values, I see that my power is good for the cost, but not good at all for the preference. So I cannot really go ahead and do this experiment because I will not have the response I want. So I need to either improve my way of measuring the preference and decrease the standard deviation, or I need to add more experiment. So when you get to 0.8 for the power, you can create your design. Then you will get the result in X. So you will have a table for the responses and a table with the design. So we can just fill up the responses and we go to the analysis. When we analyze, we have two different ways of analyzing, so the classical DOE way and the PLS analysis. So here we have an example with classical DOE, and we are only looking at the main effect. And you will get a table that will tell you what are the variables that are significant. So here only two variables are significant, the temperature and the chocolate content. Then we have a new diagnostic table which can help you to see if things are going well or not. So, for example, here on the residual, I can detect that the center sample have a high residual compared to the rest. So I can probably think that I have a curvature effect. Same thing here. I can see that the order of the experimentation. So maybe there is a bias at the end. So different explanations that are possible here. You can directly extend the design if you want to, and go through an optimization design. So here we select this one, and you can get response surface. So that's how you will be able to find out the best condition for your process or for your product. So that's how you optimize. So to conclude on this DOE part, DOE helps you to create or to improve a process or a product, and it's a very structured way of working. The next part is about predicting quality at an early stage and classification of raw material and batch attributes. So you can visualize groups usually, for example, in a PCA score plot, you can see different groups of samples. Or you can do a clustering and you will have all the samples that are close together related to each other. But if you really want to classify, you will need to make a model. So to make a model, we have in Unscrambler X 4 different options. We have SIMCA, which uses PCA models. And then we have PLS Discriminant Analysis, Super Vector Machine, and LDA. So here I'm just going to present you two different classification methods. So the first one is SIMCA, which stands for Soft Independent Modeling of Class Analogies. So what you have to do first is to make a PCA model on each class. So first you do a PCA on the total groups, and you see that the groups are quite nicely separated. So then you can do a PCA on each group. And when you look at the PCA model, so here in this graph we say that we have only one PC that is significant for each group. So it's to make it simpler to visualize it. So then we look at the center of each model, and we take two distances. So we take the maximum distance to the model, and we take the maximum leverage. And that will give us a volume. So we have some volume that if a sample falls into one of these in this volume here yellow, it will be part of group A. If it falls in the purple volume, it will be part of group B. If it falls in the white area, it will be part of none of them. So here we project our sample, and it will be part of group B. So we have an example dataset here with 5 different raw materials, and we are going to use 4 to make a model. So what we do is that we can see that all the different groups are well separated. So we can do a PCA model on each group. So this is what is done here. So here, as you see, the models don't have always the same size. So here we have 3 for the model AciDiSol and only 1 for DKP. But then we can try to classify 16 samples. So we will try to classify them, and well, as you see, the first one is classified in the group AciDiSol, which is okay because this sample was an AciDiSol sample. For DCAP, it works as well, and for this collidant sample, it works as well. All the samples here are foreign samples, so they are not part of any models. So it's normal that they are not recognized in any model. That's a good thing. The only problem here is that sample that should be recognized by the PCA model MCC, and it's not recognized. So then we can have a look at it and understand why it was not classified there. And basically, we have this plot that shows us that MCC sample is just too far away with this leverage, so it's an outlier sample. It's something that is a bit too different from the calibration sample to be classified as an MCC sample. The second method is a partially square discriminant analysis, where here each class is represented by a vector of 0 and 1. So if a sample has the value 1, it means that it's a member of the group, and if it has a 0, it's a non-member of the group. So here I had 3 groups, so I make 3 variables, A, B, and C, and I will put 1 in front of, in the column A, in front of the sample that are belonging to the group A, and then 1 in the column B for the sample of the group B, and same thing for C. And what you do is that you make a PLS model, and you will get 3 different models that will be predicting the if a sample is inside the group A, inside the group B, and inside the group C. So here all the B and C sample will get a value very close to 0 for model A, and the sample A will get a value close to 1. So if we take again our example, we have then 4 different category variables coded into 0 and 1. So after 5 components, we have very good model for all the different groups. So we can use that for the number of components. And here we have the model AciDiSol, and as you see, all the samples with that are AciDiSol will get a value very close to 1, and all the rest a value close to 0. So when we predict, we use a PLS model, and same test samples. We have 16 test samples. So when you predict, here we have the model AciDiSol. We get that the AciDiSol test sample has a value close to 1, and then the other samples that were included in the model, that they had some sample of their type in the calibration samples, they get a value close to 0. But the ones that are foreigner samples, they get a value that is about 0.5, but with a very big uncertainty. So here you cannot trust those values. So you should think that they are not part. They are not of any of those categories. Here what happened is that we have MCC that is well classified, even though it gets a value very close to 1.1, so a bit higher than 1, but it is classified in the right group, so compared to the SIMCA method. What we can see on this plot, which is Inlier versus Outlink T2. So basically we are trying to see if we can trust all the samples that we are predicting. We see that we have only 3 samples that are belonging here, and the empty sample actually is above this line, which means that it's an inlier, and all the foreign samples are outliers, so we cannot trust the fact that we get a value of 0.5. They should not be getting any value really. So to conclude on that part, MVA can be used for classification and characterization, as well as quantification purposes. So in this way you can get a value that can tell you if you are in the right track in your process at any time. Usually you will get a specific predicted value or a group, and you always have a diagnostics tool to understand your results. And if you do the analysis at different stages in your process, and you get that something is going wrong at an early stage, then you can directly stop and correct for the deviation, and so that you can decrease the cost of waste or reproduce. So to conclude on this presentation, the objectives usually that you have when you are working with your process or product is to understand what is going on, make some classification, improve or produce a new product or process, find why something has gone wrong, or predict the quality. And all that can be solved by different MBA tools, like design of experiment, statistical hypothesis, exploratory data analysis, so mainly PCA, some regression model, some classification and prediction. So if you take some general conclusion, multivariate analysis gives you a global picture, and it's an understanding tool that also helps you to improve things. So the benefits, multivariate analysis in the Ensembler X help you a lot with team working because of the project architecture, the notes, and the information that you can store on each data table or model. It also helps you for reporting your work. The plots are very informative, and there is a report generator included in the software. Before finishing this presentation, I just want to tell you that we have archived webinar, so you can go on our webpage, and under the training section you have webinar, and you have upcoming webinar and archived webinar. So you can see some webinars that has been broadcasted before. Just about Camo presence, just to say it's a global company with 5 main offices. The head office is in Norway, in Oslo. We have an office in Woodbridge, in New Jersey. We have an office in Japan, Tokyo, and one in Sydney, Australia. As well as we have an office in Bangalore, India. And then we have plenty of distributors all over the world. So now I can take your question, if you have any. Just send me a message on the panel.